Now? Oh, okay, so there's something I can turn off here, isn't there? No? There are all sorts of stories of speakers who finish their talk and then go to the toilet without taking their microphone off. So please remind me at the end to take my microphone off. Hey, the other thing is, I don't want to use the projector at all. So, is it possible to turn off? No, the other way around. Up.
As you know, the theme of this 13th discussion meeting on harmonic analysis is interplay between ergodic theory and harmonic analysis. And Professor Anthony Dooley of University of Bath, UK, will give these thematic lectures every day at the same time of this discussion meeting from 11:20, and this is the first lecture of that series. Interplay between ergodic theory and harmonic analysis. Professor Dooley.
Thank you very much. I was very pleased 18 months ago when I had the invitation to speak at this conference, because I started life as a harmonic analysis, and I've done a lot of harmonic analysis, but a second theme in my research has been ergodic theory. And I think a lot of the people here who have seen some of my work in harmonic analysis have not seen what I've done in ergodic theory. And vice versa, there are people in ergodic theory who have no idea I work in. So for me, this is a fantastic experience to be able to put together these. I've always said I have a split personality. I can put the two halves of my personality back together again for this conference. So I'd really like to thank you for allowing me the opportunity to do this psychological healing that is going to take place, I hope, over the next few days. That's the really positive thing. The downside is when I came to write down, there was a lot of stuff there that I want to talk about. So it's hard to know with these thematic lectures to how much to aim them at students and how much to aim them at the professors. And I'd like to really pay homage to B.V. Rao, who has given some great warm-up lectures on harmonic analysis to the students here in the last week. They align very much with what I was going to say in today's lecture, and I think that they'll make a great background. Now, the other thing is, given that here is all the information about setting up your computer account, and I'm about to rub it all off, and I'm sorry to the people who wrote it there, but has everybody in the room that needs to got enough information here?
Just 10 seconds.
10 seconds, okay. So I'll start. I guess that ergodic theory is. I was also trying to get some string to tie these curtains back so I could have an extra 6 inches of board space. A man might come with some wire or something. What's ergodic theory? It's the mathematical study of long-term average behavior of systems. That's one definition anyway. So usually we think of X as a set of states of the system, and T, which is some kind of a transformation, which you can think of as the elapse of time. So you can think of Tx equals the state at time 1 if it starts at x times 0. So there are two components. There's a set of states and there's a sort of dynamic. Or maybe you've got Ts, where S is a real number, which is a kind of these were the, which is a flow, I guess, that's a flow of R. Right, now I'm going to rub off this Actually, you can think of, if you have a single transformation, like I said here, this can be thought of as an action of Z. So in that context, where you have t to the n, and here's an action of R, so we are harmonic analysts, we're used to groups, and there's a clear generalization of both these things, which is a more general group so we have a whole bunch of transformations, one for each element of a group, with T of G, T of H equals T of GH. And so ergodic theory certainly started off with just Z actions, then it became flows, but these days, for the past quite a long time, 30 years or something, people have been working increasingly on group actions. And that's going to be the theme of what I'm going to discuss for you today. And it becomes quite interesting as you move from Z first to amenable groups and then to non-amenable groups. We'll see what the ergodic theory looks like in increasing generality over my lectures. So that's very waffly at the moment. We need some more conditions on X and T to say something. So here are some contexts. X could be a topological space, and T a homeomorphism. Then we get topological dynamics. And that's a very large area of study with fractals, chaos, et cetera, et cetera. I'm not going to talk about that. You can also have X being a differentiable manifold and T a diffeomorphism. It's differentiable dynamics, I guess. Again, this is, a large field, but I'm not going to say things about that. Here's where my interests lie. X mu is a measure space. And T is a bimeasurable transformation. So by bimeasurable, I mean T is invertible and T inverse are both measurable functions. So this leads to ergodic theory. These three approaches actually overlap, and a single example can often require, use of all three of them, and can be seen from different points of view. The circle, for example, you can think of it as a measure space with irrational rotations. You can think of the flow of it. You can think of it as a differentiable manifold. And often all three approaches need to be used to understand things in full generality. So anyway, let me make the basic definition of where we've got xb mu. B is a sigma algebra of measurable sets on X. Usually it's a complete probability space. Yes, you can do infinite measure theory where mu of x equals infinity. I'll mention some of that in passing, but most of the time I'll be concentrating on probability spaces. T is a bijection. T and T inverse are measurable. And T to the minus 1 of the sigma algebra equals T of the sigma algebra. What about the measure? So T is measure preserving. Means that T minus 1 of B, E, if I measure that, I get the same answer as measuring E. And T is non-singular, means that mu of T minus 1E equals 0 implies mu of E equals 0. Maybe I'll say if and only if. So traditional measure theory, a large amount of it is in the measure preserving case. There's also quite a deal of non-singular theory to which I've contributed, and I'm going to talk somewhat about that. So if we have a locally compact group, we assume that we've got TGs which satisfy all these things, either measure preserving or non-singular, in fact, such that if you look at the map Gx goes onto G dot X, well, that's a map from G cross X onto X is measurable. So you do need some crossover relationship between the G and the X. So generally we assume that that's a measurable map. So what are the basic questions? So now I can be more precise. Ergodic theory is the study of these kinds of systems. Traditional ergodic theory had Z there, then R there, and now these days we've got G there, where G is a locally compact group, and that's where harmonic analysis enters very clearly. So what are some of the basic questions that you ask? So let's think about orbits for a little while. Orbits are central to ergodic theory, obviously. So see, here's where I'd like a little bit more room there. Is it better if I do that? Am I writing large enough so that the people at the back can see? Am I speaking loud enough so that the people at the back can hear? Yes? Great. Or did you find something? Well, you can just stand up there and... So the orbit of X is a clear thing that you need to really worry about. You can think of X as being a state. TGX, or certainly in the case of Z, TGX is a complete history of that state from the infinite past right up to the infinite future. You can think of states as being think of the stock exchange as a dynamical system, then this would be all the transactions of the stock exchange encapsulated from back when it began right up till when it finishes. Or, I mean, actually ergodic theory arose from statistical mechanics, so I think of a gas and how its evolution from what it looked like to what it's going to be like in the future. So B can be thought of as the observable of events. T, the dynamics. And a measurable function is some measurement of the system. And so you're often interested in what happens to f of x, the sequence f of x, f of tx, f of t squared x, which is what happens to your measurements as time elapses. And in particular, we're interested in the long-term average behavior. Where ergodic theory began, I suppose, was the study of long-term average behavior. That's the long-term average. As n goes to infinity, what happens to this? So, basic question number one is, do these averages converge? If I call this f tilde of x, no. Does f tilde of x equal the limit as n goes to infinity, 1 over n, sum of f of t to the kx exist? And, you know, if I have to have some conditions on f, what do I know about f tilde? When can I say it exists? So that's the first question that people asked. You can think of it as something coming maybe from statistical mechanics. I have a gas, its temperature is what you're measuring. What happens to the long-term temperature? Yes? Sorry, I didn't understand that. Well,
there is a symbol t which is a bimeasurable function.
Yes.
Saying when we are looking at it impacting on the system.
Yes.
So are we taking the two things together?
Oh, right now I'm going back to the beginnings of ergodic theory when we just have a single variable t, and z is the group action, and so t to the n, I'll write instead of tg. Right. What? F is some function. It's a measurable function on the system. So when we had Z, this is where we began. It's quite interesting to know what you replace that with a general group. And in fact, I'll be talking about amenable groups and Fellner sequences in a little while to show you how you can generalize that. But my first aim is to explain to you the beginnings of ergodic theory. So von Neumann proved in 1931. Proved an L2 version. So if F is in L2, then this thing converges in L2 to a limit. And then in the same year, does Birkhoff might have an H there as well? I'm not sure anymore. He proved a pointwise. So not only does it converge in L2, but it converges almost everywhere. So this is related to what the physicists thought about. And these will be the first two. I'm kind of giving you a little bit of these will be the first two sort of results I'd like to talk about in the thing. But the physicists had something called the ergodic hypothesis.